All right, everybody. I think we can start now. Uh, Welcome again to this second class. I'll do a brief review and then we'll move on. So we started by introduction to derivatives. We talked about call options. These are the most popular ones: call option, put option, interest rate swaps. There will be other things like future forwards and all. We'll probably discuss them at the right time, and then more sophisticated derivatives. But call option, you remember, it's an option, not an obligation to purchase an underlying asset at a specified time t for a specified price k. So I've given this option to you. What's it worth? How much should you pay me for it? That's the kind of question that we've been answering. There's a European call option which expires, which can be exercised at a particular time. American call option which can be exercised anytime up to a particular time. But if you're like me, you rarely find time to exercise. That's just the way things are. All right. So you saw this payoff of call option. So let's just move on. And then the point of here was that their options can be far more sophisticated of all sorts, right? And they can be far more complex than when I mentioned here. They are very customized, um, just to meet the risk profile that the client is comfortable with, and the price that the client is comfortable with. Um, so we need a methodology to price all of these options, all these very sophisticated options. That's what this course is broadly about to the first order. Right. And as I said, it's how do you price an option? Price of the option is the price amount you need to hedge it to protect yourself from the risk from it. So really what we are also thinking about is how to come up with a hedging strategy. All right. So we said that underlying ideas are no arbitrage principle, and we first illustrate them in the simplest possible setting. So two securities, two time periods, two scenarios, right? Two, two, two. So we discussed all of this, and the idea was that option gives you some payoff here and here in those two scenarios. You can invest in the risky security, you can invest in the riskless security in the way that you exactly match this payoff. So two equations, two scenarios, um, two variables, two equations, so you know exactly how to solve for X and Y. And that tells you what portfolio you need to exactly replicate the option. Now the portfolio will have some price to construct. That's the price of the option. That's a big idea. We just keep on coming back to it. Right? All right. So you can look at all this stuff. The slides are they up, Aman?
Yes.
Okay. So you can see the slides. All right. And then, if you want more accuracy.
होमवर्क करो बच्चा इसमें ग्रेड होता है बच्चा
Hi, Ajay. Any language. All right. So go ahead. So we'll carry on. So two period, we can refine this. And really, as I mentioned, if you use, people actually use these binomial trees to solve for option prices. They just, in an automated manner, refine much further. Um, right? So you can go like 100 time steps, for example. Okay, so this was just, the point was you want to see what the option will pay in this scenario, in this scenario. So that tells you how much of risky security and risk-free security you need in this scenario. You solve the same problem here. Then you know that option is worth so much in this scenario, so much in this scenario. And you can solve, again, two equations with two variables in this scenario and construct the replicating portfolio. And what you've gained is a strategy. You start with some money and some investment in the risky asset here. I mean, you pay some money and make some investment in the risky asset here. And depending upon how the world evolves on every sample path, I mean, this is a simple model, but you're going to have complicated sample paths. On all sample paths, you know what to do. You have a prescription of exactly how to, invest in the risky and the risk-free security so that you exactly replicate the option. So if you sold the option to somebody, whatever you owe, whatever your liabilities are on the option, you exactly replicate them with the portfolio you have.
Professor, I have maybe some very basic question here.
Sure.
So one thing is that you said the way you are creating that risk-free portfolio is what if I had invested in that 1.03? sorry, 30% interest security, and what if I had bought some stocks, which would give me exactly the same value as my call option, right?
Right.
So, but I think in the put option, you do the opposite, right?
Not the opposite. You have different liabilities, so you do, you do a different calculation, but it's not the opposite.
Okay, okay.
Yeah.
And for all this to happen, I have to know all the possible prices upfront, right? If I
Yeah,
don't
you
know
have
what
a
are the possible, sorry, yeah.
no, no, exactly. So you have a mathematical model, you played out all possible scenarios, and you figured out in each possible scenario, how much risky security you need, how much
Mhm.
the value of the option. Yeah.
So in that, so that means have to know all the possible scenarios upfront, right? So for
Correct.
example, in this case, I know that there are only three possible prices at the end of step two.
Right, right, right.
Oh,
True. So you need to construct a model more complicated than this, and in the model, on every sample path, you need to know what to do.
understood.
Yeah. But this is you do upfront. And then once you've done this, then you observe the world as it evolves. So you will see one scenario in the world when you actually live it, but you know what to do at that time. So is this part clear?
Yeah.
Chalo, so let's carry on. All right, so I think we should now, so this was just to kind of illustrate the fact that you can have path dependent option, depends on the complete path, not just on the terminal stock price values, but on how you got there. All right. And then we kind of moved on to the fact that this option price that we've determined by this computing the value of this self-replicating, self-financing portfolio, one can actually also estimate compute using another calculation, and that simply involves finding the risk neutral probability. Probability which makes the risky security have the same rate of return as risk-free security. And the idea is that by having both the securities moving at the same rate of return, you get great deal of simplification. Right? In particular, any portfolio you construct of them will also move at the same rate of return. And we know in this two variable, two scenario setting, we can construct a portfolio for any option whatsoever. Right? So for every option, there exists a portfolio which exactly replicates the value of the option in every scenario. Right? And now we are saying that portfolio and hence the option price process itself when is increasing at the risk-free rate of return. So when discounted, option price process itself is a martingale. So that was the kind of big conclusion. And that's again the big idea that we're going to play with in this course. All right, I'll have you kind of look at these things on your own because we discussed them last time, but let me just go on now to the next lecture. Go ahead. Ah, one of these two is the right one. Right, this is the right one. Yeah. All right. So what we'll do now is I'll do some basic probability, but in the simple discrete setting. And here my intent is simply to get you familiar with martingales in the simple discrete setting. We'll do all of this again in more generality in continuous setting in a few lectures. Yeah. That's right. Yeah. Sorry, I missed your last point. Yeah. Yeah. So we'll make these ideas very crisp when we come to continuous setting. But yeah, all the kind of paths in the continuous setting which are assigned positive probabilities. So it doesn't matter what the value of the probabilities are. The option price will still be kind of independent. It has a very nice kind of flavor in continuous setting for those of you who know stochastic differential equation. Stochastic differential equations have a drift term and a diffusion term. So the drift term will not matter in option pricing. So diffusion term tells you how spread out your stock price is, which is like how spread out your binomial tree is. So that does affect the price. But the rate of return, the probabilities with which you move on the tree, that in the stochastic differential equation depends on the drift term, and here it depends on these node probabilities, and price is independent of that. So it's a great point. ठीक है. So so sample space mu n omega n contains 2 to the power n outcomes. It's a very kind of, nice sample space to keep in mind. Uh, so each outcome here is omega 1, omega 2 through omega n, where each omega I can take value either heads or tails. So your sample space has basically 2 to the power n outcomes, if n is the number of omegas we are considering. Right? And this tree is a nice way of seeing this. So each path here is an outcome of a probability experiment. So this is how we start with probability, right? We assume there's a sample space, we specify all possible outcomes, and then we assign probability to each of those outcomes. We put kind of mass of sand on each outcome so that the total sand that we put is equal to 1. So total probability that we assign is equal to 1. Probability assigned to any set is just simply the probability assigned to all the outcomes in that set. And the sand we put is non-negative. There's no negative sand here. All right, on top of this, now we can, on a probability space, we define random variables. So you should know that random variable is just a function. On every outcome, it gives a number, right? So any function or every outcome which gives a number, that's a random variable. So in this picture, I've given you many random variables. There's S0 random variable. Now S0 random variable has value 4 on every outcome, right? Whichever path you take, whether you go here, S0 is always going to have value 4. So this is a deterministic random variable. It just takes one value. On the other hand, S1 takes two values, right? S1H. If the first coin toss is heads, S1 is 8. If the first coin toss is tails, S1 is 2. It doesn't depend on what happens with other coin tosses. And now you can simply see S2 as well as S3. And what you're also seeing from here is that kind of information propagation. So when we are valuing S1, we have less information. We have information of just the first coin toss. For S2, we have two coin toss information. So this is going to be very important when you think of stock prices. We'll have this kind of time evolving and our amount of information is increasing with time. We know more about stock prices history as time increases.
How are we defining SIs?
SIs here are just stock prices.
So it's just okay.
Yeah. I mean, just a model. Suppose you start with 4, with some probability you can take value 8 or 2, so on and so on. Yeah. So we'll play with this maybe. You see this example, I think, is in Stephen Street Volume 1. All right. So S1 takes 2 values, S2 takes 3 values. Now, once we understand the idea of random variables, we also have this idea of expectation, right? Expectation is simply this quantity right here. It's all possible values that the random variable takes, weighed by the probability of taking those values, summed over all sample paths, overall outcome. So that's the expected value of X. Again, it gets its kind of prestige and value and usefulness from law of large numbers, which says that if you have many samples of this random variable, independent sample, you take the average begins to look like the expectation. All right, so this is one example for you. This is a sample space with 8 outcomes, HHH, HST, so on and so forth. And with these probabilities 0.1, 0.2, 0.15. And the question for you is, I can't hide it, what is the expected value of S2? So S2 is a random variable which takes how many values?
2 values. Sorry, 3 values.
S2 takes 3 values, right? So it takes value 16 with what probability?
1 by.
No, well, it should take with probability when heads happens.
It's 1 by 0.2.
Heads, as well as heads, tails. 2 outcomes, right? But I've given you these probabilities here. So it's 0.3 in this example, right? And then you have S2 taking value 4, and that it takes when you see H, TH, HTT, THH, THT. So all these probabilities come here. And then you can have TT, that can happen when you have TTH or TTT, 0.25 probability. And with that, the random variable takes value of 1. So you're with me on this so far, right?
Oh, I said 1 by.
Yeah?
S2 contains 16, right?
S2 must be there.
Yeah, it takes
Right,
us
yeah.
16
I mean, you have to realize it takes whatever values I tell it to.
Pi will be multiplied by 0.1 plus 0.2.
Oh, that's
So-
he's defined the problem.
But HH.
No, so this probability as well as this probability, right? Two outcomes corresponds to HH. And it's HHT and HHH.
Oh, okay. So H will only looking at.
HH is actually a set of two outcomes.
Yeah, I was
Yeah.
thinking you're only stopping at that.
No, no, no. So yeah, it's good to be very clear on these things.
That.
Right? Yeah.
So what is the probability of HH 0.25 would.
Well, I've defined these probabilities, right? I've given these probabilities here, right? So if I'd given them like before, then it would have been 0.25. But yeah, this is the whole point that probabilities are up to us. And it's an important point because, a lot of mathematics gets done by just playing with having different probabilities on the same sample space. And you put different probabilities because the math simplifies. So it's good to get familiar with these things and, what does expectation really mean? Okay, a big idea we're going to play a lot with in some generality later is conditional expectation. Right now, I'll just give you a feel for it. So we know this thing, right? This you've seen. Probability of x equal to small x given y equal to small y. When we have x and y dependent variables, is just the joint probability of x equal to small x, y equal to small y over probability that y is equal to small y. There are technicalities that, okay, if the denominator is 0, then the whole thing is 0. All right, and then with this probabilities, we know basically what's happened is we've got more information. We've learned that y is equal to small y. That has changed the probabilities of our universe, right? And now when we find the expected value of x given y is equal to small y, we find expectation with respect to these new probabilities, right? That's our elementary understanding of conditional probabilities. Yeah. So what's that?
There's no independence.
Right now, there's no independent, yeah. In this particular example, I mean, when I say dependence, independence is a special case of that.
Also, Prof, would this be marginal expectation over X?
It's no, it's conditional expectation, I guess, given y equal to small y. So it's a function of small y. As small y changes, it changes. In some sense, you can think of this as a random variable, the conditional expectation, which is a function of random variable y.
Okay.
That's the correct way of thinking about it, as we move forward. But for now, let's just look at this quantity right here. What's the probability of seeing all of omega, given that you've seen a path up to small n number of steps, right? So this is just again, the joint probability of seeing both these things, and that's just probability of seeing omega. I'm assuming omega 1 through omega n belong to this big omega here, over probability of omega 1 through omega n. So this is the conditional probability, and now we can come up with, so this is notation I'm going to use, conditional expectation of x given omega 1 through omega n. So I have transferred, I have evolved in this world along the path of small omega 1 through small omega n. Now what's my best guess for x? What's my expectation of x, right? That will just be all the values x omega can take on the remaining paths. I fix the paths that I've seen, and probability of, conditional probability of taking those values omega, right? So okay, so let me just see what do I want to say in with sequence. Let's just come here. You could, for example, condition on this event, right? You come on this path. And now you can say, okay, what's the expected value of S3 given this? Right? I've been on, so just looking at this picture, can you see how you would compute S3? I've seen this path already. S, it can take either this value or this value now, right?
Yeah, 8 with some probability and 2
2 with some probability. And these probabilities are going to be conditional probabilities, right? So we'll just do that in a moment. I'll just say one point here. This is the definition of conditional expectation. Notationally, these things get very cumbersome. So after a while, we don't show omega 1 through omega small n, right? But it causes confusion if you're not used to this. So you should always remember when we show conditional expectation, it is, there's a underlying omega on which it is defined. So I'll use this en of x to denote that we are conditioning on small n number of steps, yeah. Basically on all omega 1 to omega n, small n, we'll have this conditional expectation. So this random will be a function of, variable will be a function of omega 1 through omega small n.
Just to be clear, we're not going to be writing the conditional sign. We'll just write here.
Yeah, en x, e sub n x. Sometimes we will, sometimes we won't, yeah. Okay, so this is just illustrating the point we discussed. So what's E2 of S3 given HT? It's S3 STH into conditional probability of seeing STH, which is just the term right here. S3 STT plus conditional probability of seeing STT, right? And now usually this is a more typical setting where this probability would look like some p times 1 minus p square. That's when we are assuming that the coin tosses are independent. So PST is p times 1 minus p and so on. We know what we are saying. In that case, things will simplify. So coin flips now are independent. Then this expectation is simply S3 STH, and you see the next path, and the next path you see ahead, and that's its probability P, or S3 STT, and that happens with probability 1 minus P, right? So this is going to be more typical that I'm here. I can just see this value or this value, this with probability P, this with probability 1 minus P, and that's what gives me the conditional expectation. So this is how you would intuitively do calculation in any case. But you just have to remember that this is true only when there's independence. When there's dependence, you have to be more careful. All right. So ES, any questions online? All right, guys. So E of S given X is basically a random variable. Expected conditional expectation of S given X is a random variable. That's a function of X, the random variable. So it's some function, let's call it f of X, right, of X, where this function itself at small x takes this value, E of X given X is equal to small x, right? But it's good to think of these guys as just random variables, which are functions of the random variable that you're conditioning on, right? Okay, and now you can show, and this you should do at leisure on your own time, or maybe ChatGPT can show you how it's done. But this is conditional expectation of S given random variables X and Y. Now that's a random variable which is a function of X and Y. That's what we discussed, right? Now you take its conditional expectation given X. So it turns out that's just expectation of S given X. It's a calculation. You can assume X, Y, Z have some joint distribution, work out the calculation, you'll see it will work out, it'll simplify. All of this you'll do in elementary discrete settings. In continuous settings, our aim is to show these expectations, these random variables in much greater generality. Then this becomes a little bit more sophisticated. So we'll see that at the right time. Well, more than just continuous settings. So general means you allow for continuous, discrete, and even more general things than that. Yeah. Sure, and this will hold, but it will, you will have to develop that kind of technology to kind of see these things the right way. But you have to keep in mind that we want to do, just like, when you do integration, you don't want to just integrate nice continuous functions anymore. You want to be able to integrate functions which, on rationals take some value, on irrational take some other value, kind of, measurable functions, not just continuous functions. So then for that kind of richness, you need to pay some price. You need to develop more technical technology, as I've been saying. All right. So now let's come to our definition. So this, just keep it in mind that this is going to be useful.
Professor,
Yes?
will it not be expectation of S given by
Uh,
just
no, given X, right? This last one is X,
okay.
right? So it should be a function of X, yeah. This is some variable, it's a function of X and Y. Condition on X should be a function of X. So that's one sanity check. All right, a stochastic process or a collection of random variables. So stochastic process is a collection of random variables. X1, X2 through X capital N. I could go up to infinity, but in finance, we are pricing options which expire in finite time. So we generally just go for finite time horizons. So I'll do that here. It's called a martingale if expected value of Xn, given the history X1 through Xn minus 1. So conditional expectation, your best guess, your expectation of Xn given all this information is just equal to Xn minus 1. right? So this is saying that on an average, you're not changing. It could be that xn minus was 10,000, but then your next guy's expectation is also 10,000. Could be that xn minus 1 is, minus 500. Then the next guy is also going to be minus 500, right? On an average, the increment, the change is going to be zero on average. So, it kind of models noise in very processes. The noise is coming up, so noise doesn't have any mean drift, but then that would be signal. So signal you've taken out. So the noise is mean zero. So that's what's captured by these martingales. You had a question?
Won't it always stay the same then? So for example, expectation.
On average, it'll remain the same. That's
The
all.
expectation.
Yeah, in expectation.
Okay.
Just like the risky security, in expectation, it's going at 3%. In our example,
Hmm.
it can take a higher or lower value.
Okay, but on expectation. it's
On
the-
expectations remain the same. So martingale is a very charming term. Um, one definition of this is it's if you understand Hindi, it's ghode ki lagam. You have this kind of saddle tied to the I guess the face of the horse. It keeps the horse balanced. It just brings the process back to the kind of mean. That's somehow that is it's called martingale. Martingale was also a betting strategy. That's not it doesn't relate to the definition per se, but let me just ask you very quickly to all you online guys as well. Suppose you're playing a fair game. Your chance of winning in a game is 10% or your chance of losing is 90%. And you can play this game repeatedly. How do you make money for sure? How do you beat the system in that game? Yeah, go ahead.
Reward is higher, that covers the loss, then gives you profit.
Sorry, what's that?
Reward is way higher, like once.
I mean, you're playing an unfair game against me. You have 10% chance of winning. I have 90% chance of winning. How do you make sure you go back home?
Chance that I win a lot, then I'm losing 90% of the time.
It's just 1 rupee you win, you get 1 rupee from me, you lose 1 rupee. Yeah, so doubling strategy, as some of you may know, that now I'm you. So I play 1 rupee, I lose. Then I bet 2 rupees, I lose. I bet 4 rupees, I lose. I bet 8 rupees, I lose. With probability one, I'll win at some time. And then when I win, I would have won 1 rupee. When you subtract all the loss and add this. So instead of, if you want to win more than 1 rupee, then just multiply everything by 10 million. Then you'll win 10 million rupees. But you need really deep pockets in that case. So these winning strategies do exist. You have people in casinos who are watching out on cameras to see if you have deep pockets, to kind of see if you're doing something like this. Yeah?
On the expectation of X and Y.
No, it's a random variable. See, I told you these conditional expectations are random variables. They are functions in this case of x1 through xn minus 1. But this is a special case where the function is just equal to xn minus 1. So this betting strategy I told you is also called a martingale. But in any case, you see martingale so much that's good to kind of get to know them a little bit more. On average, it is not changing. So let's take one example of this, y1, y2 through yn. Let's say they're independent with mean 0. Right? They're independent of each other and they have mean 0. Now, in that case, expected value of Sn plus 1 given y1 through yn. So if I know y1 through yn, then I know Sn. And what I know comes out of conditional expectation. I'm not proving it. I'm just assuming that you can consider that plausible. So Sn comes out, and then you're left with conditional expectation of yn plus 1 given yn through yn. Right? And because it's independent, the conditional expectation is same as the expectation. That again, it needs to be checked, but we've grown up with these things, so we accept these things, right? So then E of yn plus 1 is 0, so you get Sn. So this is an example of martingale, right? It's an example of a fair game, where the winnings that you have on an average are 0. Right? So martingales capture the idea of a fair game.
Should, like, in Sn, when we're adding Sn plus expectation of yn plus 1 given some up to yn,
Yeah.
in the end, then we're coming back to Sn. Should we like add something more?
No, this guy is 0, right? This guy here is equal to 0. This guy is what remains.
Okay.
Right? Is this clear to everybody? All right, so hence this is a martingale. Let me just give you a very quick one more example. So now suppose expected value of yi is equal to 1, right? And yi's are independent. And now you look at mn equal to the product of yi's, I equal to 1 to n, right? So now let's look at the conditional expectation of mn plus 1 given y1 through yn. So since y1 through yn is given, we know it, and hence mn we know, and it's independent of yn plus 1, so it comes outside, right? And expected value of yn plus 1 given yn to yn, because it's independent, it's just expected value of yn plus 1, which is 1. So when you have mean one random variables, then their product is a martingale. Now in reality, so we'll see a lot of this for independent, In reality, you'll typically assume that yi's are non-negative, and there's some more conditions required to define a proper martingale, in a more general spaces, but we'll cover that when we get there.
Just to summarize, for mean 0 random variables, this
Additive.
term is a martingale.
Yeah,
And for mean 1, the
product is a martingale. That's correct. Yeah.
I have a small doubt, Professor. In the summation, you explicitly mentioned that yi's were independent.
Right, right.
In product, do we not need them to be independent?
I mentioned that.
Oh, sorry.
I don't write it. Yeah, no, I mentioned it.
Okay,
Yeah.
okay, sorry.
In my mind, I wrote it. Okay, so anyway, yeah, it's there. No point writing it here. I'll write it in the notes maybe. Yeah. Okay, so where are we now? Yeah, so other fact is this. Now suppose x1 through xn is a martingale. That means e of xn plus 1 given this information x1 through xn is xn. Now let's look at expected value of conditional expectation xn plus 2 given xn2. No, I guess what I'm saying now is as follows. What I'm saying is that this xn plus 1 is seen to be equal to conditional expectation of xn plus 2 given x1 to xn plus 1, because it's a martingale, right?
Yes.
Right. And now, we've already discussed that this information is more than this information. So this reduces to xn basically. Okay, so now that I see it, I think it requires a little bit more argument, but let's accept it from our previous
And
discussion.
this we're taking it from the previous results that we show earlier.
Previous, which I showed you.
Yeah, expectation of some event given x, y, and then
Yeah.
given x is
Yeah.
just expectation of that event given x.
Right, right. I mean, what I could have, I need an extra argument to complete the loop,
Isn't
but
it
if you don't mind, I won't show it right now.
expectation of x plus 2 given that which is x n minus 1 because it's martingale. You can just take the red part.
I mean, your point, I guess the point is, all I can show from this is that e of xn plus, this whole thing here is expected value of xn plus 2 given x1 through xn. So then I need one more argument to argue that that's xn.
But can't you see the red part, like expectation of x plus 2 given x1 dot xn plus 2?
That's, I'm just going back here, yeah.
Yeah.
Oh, that's right. That's
That is
right.
xn.
Yeah. So there's no, sorry. So this already I have here. So what's kind of bothering me?
That red is.
Yeah, no, so I'm perfectly fine. No, thanks. This is the next line here. So I guess the point is, from this part here, that plugging in the value of xn plus 1, we get this expression, right? And we get that this expression is equal to xn. And now from our earlier result, we get that the left-hand side is equal to this quantity right here, right? So yeah, this is precise, and that's equal to xn, right? So not just conditional expectation of xn plus 1 given x1 to xn is equal to xn, but conditional expectation of xn plus 2 given x1 to xn is also equal to xn. So what that means, you can generalize now by induction that expected value of conditional expectation of xm given x1 through xn is equal to xn for m greater than n, right? So not just are you staying, if I'm at xn, not will I be at xn in the next step on average, I'll be at xn for however many steps in front on average. That's the property of the martingale. So everybody's with me on this, right? This is also going to be useful in a moment. Okay, now let's come back to our stock prices now that we have some understanding of martingales. So now I'm looking at this model where S0 goes up to U times S0 or comes down to D times S0. And at any node, it either goes up and increases by a factor U or comes down and decreases by a factor D. That's a nice model and it has nice uniform structure. That makes things easy. Okay, so
Sir?
SN, yeah.
So how large n we can take in order to satisfy this property expectation of xm given x1 to xn for
True for
m
every
greater than or equals to xn?
True for every M. In our case, because we
Oh,
are restricting our M to big N, we just go up to big N.
okay.
But otherwise, for martingales, if they're defined for time index going to infinity, this will be true for all times. Okay, all right, so Sn is just, U times number of heads till time in n steps, D times number of tails in n steps times S0. And now from our earlier argument, because at every node you can kind of see that if you didn't have 1 plus r between D and U, you will have an arbitrage. So 1 plus r must be between D and U. R is the discrete rate of return. Okay? So what we achieve by this is that we can now define this quantity P tilde this quantity right here. What can I say about this P tilde here? Anybody? Well, that we'll come to, but can we say something less than that? Can we just say it's a probability? So it's between 0 and 1. So it's a probability, right? And Q tilde is also a probability. Okay. So now let's look at the conditional expectation of Sn plus 1 given the sample path omega 1 through omega n under these new probabilities, these neutral probabilities. These new probabilities, let's just call them right now. So because, and what we are really assuming here is we're assuming that these coin tosses in this tree are happening independently. So when I give you P tilde measure, I mean a measure where probabilities of paths corresponds to, P tilde into number of raised to power number of heads, Q tilde raised to power number of tails. Okay. So in that world, we know that this conditional expectation here is simply going to be U times Sn into P tilde plus D times Sn into Q tilde. Right? You can only take two values up and down with these probabilities. Now I'll simply simplify these things here. So you just follow this calculation. Can you reach this? U minus D is common. UD cancels with UD. U times 1 plus R minus D times 1 plus R. U minus D cancels, so you're left with 1 plus R into Sn. Right? So that tells you that with these probabilities P tilde and Q tilde, just like in the 2 time period setting, you have the property that Sn plus 1 is increasing at the rate 1 plus R. And hence, conditional expectation of Sn plus 1 divided by 1 plus R raised to power n plus 1, given this information, is just Sn divided by 1 plus R raised to power n. Is this kind of clear? I've just taken this equation here that I had, this guy and this guy, and just divided them by 1 plus R raised to power n plus 1. Right? And what do I conclude by this? Anyone? What does this equation help me conclude? This thing right here? Discounted stock price process is a martingale. Sn divided by 1 plus R to the power n, that process on an average is not changing. It has this martingale property. That's what I've been saying earlier, that you find the probabilities under which the stock price process increases on an average at the rate 1 plus R, and hence the discounted stock price process is a martingale. Okay, good. So now we've established that if we choose our P tilde Q tilde probabilities, we have this nice property. Now let's move further. Let's consider a portfolio that has xn wealth at omega 1 through omega n, right? It purchased delta n amount of stock, delta n number of stock, and delta n depends upon everything that's happened so far. It depends upon omega 1, omega 2 to omega small n. It can't look in the future. It should not, like. And invest the risk in risk-free rate. So what's going to happen? My portfolio will be delta n into Sn. Well, after one time period, it will be delta n into Sn plus 1. And this is the wealth I invested in the risk-free rate, Xn minus delta n Sn. That's going to become 1 plus R of this, right? That's my wealth after one time period. Okay, so what can I say about this conditional expectation? Conditional expectation of portfolio value at time n plus 1, given all the information till time n. So I'm just taking conditional expectation of this guy here. So now delta n is known to me at time n. So from conditional expectation point of view, it's a constant. So it comes outside the conditional expectation right here. These are things you've seen already in some form. And then what I'm left with is just the conditional expectation of Sn plus 1 from this term right here. And from this guy, this whole thing is known to me, so it just remains the same when I take conditional expectation. This doesn't change. And now what can I claim here? Right, it just 1 plus R into Xn remains, right? Because this becomes Sn.
Yes. And so that cancels out to be
Right, so that cancels out. So basically, it's kind of, it's essentially saying, it is exactly saying, yeah,
So when you bracket for the R type n minus delta and Sn,
yeah.
you have a term R delta and Sn also. Minus R delta and Sn.
Right. So what happens to the conditional expectation of Sn plus 1 given omega 1 through omega n?
Becomes Sn.
That becomes Sn times 1 plus R. Right? Sn plus 1 is increasing at the rate 1 plus R.
Right.
Discounted, it's still remaining Sn. So it exactly cancels here. Right? So then you have exactly 1 plus R into Xn. So what do we conclude? This is equal to this quantity right here. What's the conclusion? You can do better than that now.
My portfolio wealth is growing at the rate.
1 plus, and hence, what can I say about the discounted portfolio value? It's a martingale. Yeah. Any discounted self-financing portfolio process. Self-financing in the sense Xn is the wealth at this time. I'm not taking any money coming from outside, or there's no money going outside. It's only Xn that I'm distributing between two. And I'll keep on doing that at Xn plus 1 at every stage. So then this process that I'll get, this portfolio wealth as it evolves, if I discount it, it becomes a martingale. I'm being a little bit quick here, but you'll find this discussion, I think, in chapter 2 of Stephen Shee, volume 1. So there he gives more examples, and also you can go through that. But this point should be clear that Xn upon 1 plus R to the power n is a martingale. So in particular, since in this world of, two scenarios, two variables, so two equations, two variables, we can replicate any option price process, any option. That means that option price process, when discounted, is also a martingale. Is this kind of clear? Because every self-financing portfolio process, when discounted, is a martingale. So hence, option price process is an example of one such portfolio process. That's also is a martingale. Okay, so what do we get from there? So
Discounted option.
yeah. So discounted option price process, Vn upon 1 plus R to the power n is a martingale. That means conditional expect. So I'm calling Vn is now the option price. At every scenario, at every state, it's a value of the option. So this property here is true. this conditional expectation, Vn plus 1, discounted by 1 plus R ratio n plus 1, satisfies this equality here. So it's a martingale. In particular, what this means is, because we know for martingales that we can go m steps, and this continues to be true for m greater than equal to n. So Vm discounted by 1 plus R to the power m, that's equal to Vn discounted by 1 plus R to the power n. So in particular, I can take n to be 0, and then the option price process V0. That's what I'm after, right? I want to find the option price at time 0. That's conditional expectation of Vn at the big N time, final time, discounted. Now, what is V of big N for options? So I'm going again a little fast. You have to read up on your own, but we need to kind of cover a lot. So, what is V of big N in the option price process?
I mean, just from that,
and,
we not into 1 plus R to the power.
It's exactly the payoff from the option.
Yeah, in the end.
In the end, what the option payoff gives. That's your Vn. So what it's saying is, what you're after, this whole exercise is about finding the option price V0. And what you're saying is V0, the option price that you want to find, is simply the expectation of the payoff from the option when discounted, but under the risk neutral measure. So that's kind of a big thing. So that relationship works out here. So we have a nice expression for option price. Now, in large dimensions, you'll see that these expectations are really integrals. So we've really reduced the problem of pricing an option to evaluating a large integral. Right? How do you evaluate large integrals? Integration methods, no, but what else do we do? Monte Carlo methods. So this opens up the whole field of options pricing to Monte Carlo techniques.
So, but does this also suggest that expectation of Vn is just V naught into 1 plus R to the power big N?
1 plus R to the power 0.
No, Vn is the expectation of Vn
Mhm.
under this measure.
Yeah, that's
V
right.
naught into-
That's right. Yeah, of course. Yeah.
So one more question to
Right.
answer. So the big picture overview.
Yeah.
So suppose I have this firm
Mhm.
and through this calculation, I find out okay, for some option, this is my theoretical price.
Mhm.
Now, if someone is selling lower, higher than that, giving me option lower or higher than that. So based on my theoretical value, now I will be able to make this transaction. कि, okay, अगर ये ज़्यादा है तो I'll buy
Yeah.
low and sell high.
Your calculation tells you the price should be 35, you sell it for maybe 50 or something.
Okay.
You keep some buffer for the model error,
Mhm.
but at least now you have a basis for doing this business.
Okay. So this will give me my intuition of what the right price should be.
It gives you a very good idea what the right price is. That if you're going to sell this option, you're exposing yourself to risk.
Mhm.
You're going to hedge yourself against the risk.
Mhm.
How much money do you need to hedge yourself?
Mhm.
If the price is telling you 35,
Mhm.
you say to yourself, okay, maybe my model is not entirely correct. I made all these assumptions.
Mhm.
So there's some error to it, but 45 I can certainly absorb.
Okay.
So yeah, you take. And if you have not one option, but maybe 10,000 options, you can use this theory to look at the kind of composite risk and exactly hedge that. So it's a very important guideline. In the world of finance, once you kind of figure out how to price a particular instrument, then the market explodes. Because then people trust each other that they know how to price this thing, that the price is right. Otherwise, you don't quite know what the risk is. Okay, so Vn here. So Vn is option payoff function. Let's call it Gn. I'm just giving a new notation. So Gn for call option was Sn minus k, the positive part, right? Okay, I just said the final time period. Gn for option. So this we probably did not do. Look back option is also popular option. Its payoff is the maximum value that the stock price realized up till that time, minus the stock price at that time. So you don't feel bad about having missed out when the maximum is attained.
So it gives you that option to go back to that price.
It gives you this payoff.
I mean, the maximum price that happened during.
That's right. Yeah.
Actually exercise that.
Yeah, so you were hoping that you wish you'd exercised at that time. So what did you lose by not exercising at that time? That's this maximum minus Sn. So it pays you that, so that it takes care of your worry, but not for free.
The price
You have to pay us.
You have to pay a certain amount, yeah. So to get rid of that worry that, you didn't time the market right, you have to pay a certain price.
What we have to pay, is that fixed? I mean, does that get decided when the option contract starts, or is that?
When the option contract starts. That's why you use all this theory to come up with the right price. Yeah? Any other questions? Or?
So what we're saying is that instead of just looking at SN, I want to look at the max.
Yeah.
So then should that be max SN minus K?
Well, it's designed to be just maximum SN minus SN. It's up to you how you design it, right? It's the current stock price. It's become popular this way. I could have said, let's have a strike price.
The point is then the GN will always be positive.
Yeah, it'll be positive. That's right.
So
You'll pay a fairly strong positive price for it.
okay, yeah.
Yeah.
Yeah, you're paying good for it.
That's right. You will always get something for it, so you pay a fair amount. It's a look back option. But your point is that why not define a call option which looks at this maximum structure? So one could.
Yeah.
Yeah, one could do that, yeah. And it is done. Okay, so this is another option that is quite common. It's called down and out barrier option. So if your SN, if your stock price anytime goes below level B, the barrier B, then you're out. You won't get any payoff from the option. So you get payoff from the option only if it remains above the barrier B, and then you could have a put option. K is the strike price, minus the stock price at that time. So you're able to sell the stock price for value K. So this is down and out barrier option. You can have all kinds of versions. Call, puts, all of that. Okay. So V0 is the option price, and option price is given as this quantity right here. Now I should tell you, let me see. Okay, let me just write here.
They should be one minus.
Hmm?
Is that? Acha, oh,
Yeah.
Yeah.
Now, yeah, minus n. It's just a discount factor. Now you can see that, Vn upon 1 plus r to the power small n is equal to conditional expectation of n Gn 1 plus r to the power n. Right? This is also true. It's a martingale process. This equation is true, which tells you that the option price at time small n is simply E tilde n Gn 1 plus r to the power n minus n. So the payoff you'll get in the future by the appropriate discount factor, because you have n minus n time periods remaining. So this is nice. You can compute these things. What's nice about this is that in continuous time, this will actually show you a partial differential equation.
Open this bit again.
Mhm.
So we say that the option price is that the top, the expectation, which makes sense.
Yeah, sorry, so what's your question?
Okay, wait, the left is small n, sorry.
Yeah, it's small n. ठीक है. No, my point is this Vn's is the option price process as a function of omega 1, omega 2, omega small n. ठीक है? Now, what we will see is that this will have a continuous version in continuous time, V of t, and that V of t, the option price process, will satisfy a partial differential equation. It'll be an equivalence of this quantity here. So these conditional expectations satisfy a partial differential equation, and these are called Feynman-Karp formula. It was basically about conditional expectations of Markov processes. So that kind of follows from this relation. I'm just building a linkage, because when you see it, you'll see what the discrete analog was. Okay, any other questions? Sure, so we'll move on a little bit to the next topic. So now I'll just show these things in a multiple securities format, not just one risky security, but multiple risky securities, right? But we'll keep it simple, just 2 time periods. I could do a multiple time period, but I'll do that in a continuous setting, not in a discrete setting. Okay. So, but this is instructive. It gives you a lot of insight into the more complicated process. Okay, consider two time period model with n securities and m scenarios. Before I go to this, let me just say a few things. I think in this course, we are budgeted for 24 lectures.
No, 26.
24, I think that's what somebody told me.
Yeah, I think 1 week is.
Holidays.
Yeah, so what I'll do is,
Weekend class on the weekend.
yeah, no, so what I'll do is, first of all, your exam quizzes will be outside the class hours. And I'll evaluate you if you want only on 24 lectures, although I'll give you 26 lectures. So we'll have 2 extra lectures and some other times as you suggested. But if you want, I'll just evaluate you on 24. Okay, so that way you don't feel like you have to do much more extra things. Okay, right. Anything else we should discuss in kind of logistical details at this stage? That should be fine.
Right.
It's on the.
Slides are already up, yeah. Yeah. This is the center website.
Both of them, it's a link on both of them.
What's the other one?
Stochastic.github.io.
I see. Okay, chalo, so now we'll start with this. Any other questions? Right. So we'll start with this. So now we are considering two time period model again. So just as we started out earlier, but now we have n securities and n scenarios. So we generalize from 2 securities and 2 scenarios. So S01 is the price of the first security at time 0. S0n is the price of the nth security at time 0. And the point is the world is now allowed to evolve in m different scenarios. Right? So it's more kind of a reasonable model. With m and n are arbitrary. And this could again happen with probability P1, P2, Pm. But as we've been saying, these probabilities are like other people's children, they don't matter at all. Okay. So now you have, I equal to 1 to n, these are securities. So ith security has value S1I omega 1 in scenario 1 and S1I omega m in scenario m. Right? So everybody with me on this? For I equal to 1 to m. I will not put this notation 1 anymore. When I don't put any subscript, just to avoid clutter. Then I mean time period 1. Each PI is positive. So what we are going to do is now these are our stock prices. Now we have a derivative security in this setup. We want to see what's the right price for that is. And we want to see if our no arbitrage principle gives us this risk neutral measure, and that way a more simplified version of the price. Okay, so I'm going to keep this guy as the matrix of, this is first security. This column is first security in m scenarios, nth column is nth security in all these m scenarios, right? That's your matrix S. Subscript 1 is hidden. Oops. Oh, this is not a PDF file, sorry. This should, yeah, no, I'll go back. Yeah. No, but well, I thought I had the PDF. Just give me 1 second. Oh, I don't have a PDF file on this. All right, so just be careful. All right, so subscript 1 is hidden. So now we'll formally define arbitrage. So arbitrage is a trading strategy. Trading strategy is just investing in different securities, theta in Rn. So we purchase theta I amount of ith security, right?
Theta I amount of ith security.
Yeah. So the wealth that we have to invest is S0 transpose theta, right? That's the amount we need to invest to purchase theta amount of ith security for each I. So now suppose I'm investing negative wealth. So S0 transpose theta is negative, so I'm getting something. Because my theta is negative, I'm selling some securities. So net, I'm getting something. And my S1 theta. S1 theta is now value of my portfolio in each of those M scenarios. And then suppose it's 0 in each of those M scenarios. Then I say I have an arbitrage. Because I got some money upfront and I had zero risk in all the M scenarios.
So
Yeah, so I'm trying to define the idea of an arbitrage. That's what's an arbitrage. So arbitrage is a trading strategy. That's the way to think about this. It's investing some money in each of the securities, theta 1, theta 2 to theta n, in such a manner that S0 transpose theta is negative, meaning my investment is such that I'm getting something right now. Because I'm actually selling stocks, I'm shorting stocks. I'm not really buying them. Okay? But I've chosen my theta in such a manner because see, this is the world that's clear to me. I know what the M scenarios are. I know what the stock price values in those M scenarios are. And suppose I know that S0 transpose S1 times theta, S1 is a matrix, times theta will just give you the value of your portfolio in each of the M scenarios. And it's zero in each of those M scenarios. So meaning in future, you have no liability whatsoever. So you get some money upfront and you have no liability whatsoever in the future. That's an example of an arbitrage, right? So,
Wait,
yeah.
wait. Your you invest in risky security.
Mhm.
In that case, just look here is S not transpose theta positive then because you invested.
Well, can be negative investment means you bought.
No, but if you negative investment is the what?
No, negative investment means I sold.
Okay,
Yeah.
so it will be positive then, right? It won't be this
No, so the way I'm thinking about this is that S0 transpose theta being negative means money is coming to me.
money.
is there a plus sign after that?
Hmm? Yeah, so if it's positive, then I've invested. If it's negative, then it's coming to me. ठीक है. Yeah, so this is kind of a convention here. Yeah.
Can you also repeat the like intuition behind S1 theta being equal to 0?
I'm just saying, suppose my theta is such that in every scenario in future, my portfolio is worth zero.
Why would you want to do that?
Suppose you do it.
Oh,
In that case, you have an example of an arbitrage because you got some wealth coming to you
huh,
and you got no wealth going out.
out.
Yeah.
Oh,
That's all. That's all.
yeah.
So we are just making it very precise what arbitrage means. It's no longer a hazy notion that you make money out of nothing. So this is one example of an arbitrage. I should not use my pen. Should use it carefully. And the other example is here, where S0 transpose theta is non-positive. So money is either not coming to me, but it's not being going away from me. It's either zero money is coming to me or positive money is coming to me. And S1 theta is greater than or equal to 0. So S1 theta, I'm thinking of as money coming to me.
That's the greater. That's the greater here. Because your it's not equal.
So not equal to 0 means it's greater than 0. Yeah. So it's non-negative and it's not entirely 0. So in some scenarios, it's positive.
But that would mean money going out.
Yeah, no, I'm interpreting it as money coming in. This is the money coming into me. Because I'm now selling the portfolio.
Can you please make a note of that in the note?
Yeah, no, I'll do that later. Yeah, I understand. Yeah. This should be very clear. I mean, this is the value of the portfolio, but I have this portfolio. So if it's positive, that's the money I get when I liquidate it.
Okay.
You see, that's the value of the portfolio. If it's positive, that's the money I have to spend to get that portfolio.
Okay.
So if it's negative, it's money coming to me. So these are examples of arbitrages. Both of these are examples of arbitrages. These are mathematically precise examples of arbitrages.
Is it just two, or is there like a general abstract?
No, we'll keep it as these two. This covers everything. Because any other arbitrage you can come up, the idea is you're making money out of nothing. You can reduce to these two.
Okay.
So still value of S1 theta should be less than absolute value of ST theta, S0 t.
No such linkage. As long as S0 transpose theta is non-positive, meaning either nothing is coming to me or something positive is coming to me. Right? To construct S0 transpose theta, I need I need to pay negative amount of money, non-positive amount of money. So something. And at the end, I get something non-negative coming to me, and in some scenario, positive amount coming to me. That's an arbitrage. So I'm not paying anything from my pocket, and with some probability, I'm getting positive amount. That's an arbitrage. Yeah.
So shouldn't we transpose and put the basis like S1 transpose?
No, I mean, the way I've defined S1, it just boils down to how I define S1, right? So if I look at theta 1 into the first security in scenario omega 1 plus theta 2 in the second security in scenario omega 1. So the first row here multiplied by theta gives me the wealth after first scenario.
Yeah, it's a column of scenarios, right?
Yeah.
Total portfolio value.
That's right.
So that is if you do S1 times.
That's it. So I'm saying that's the right calculation.
Yeah, okay, so then, okay, so.
S0 is just this vector right here. S0 transpose just means, S01 is the value of the S0 security, first security times. Yeah. All this should be correct because I've taken from somewhere. Tried and tested. Okay. Now you have this elementary security that I'll define, and this is just a security which gives you 1 unit in scenario J and 0 unit elsewhere. It just clarifies thinking to have these elementary securities. So it's, purely scenario based. You get 1 unit in one scenario, 0 elsewhere. This is called E of J. So let's keep that in mind. A security, so we are just setting the stage here. We're giving you definitions. A security or a contingent claim or a random variable is said to be attainable if there exists a trading strategy theta such that security X or a contingent claim is said to be attainable if there exists a trading strategy theta so that X is equal to S times theta. So if I can, X is telling me is a security which is telling me wealth in different M scenarios. 2 units in scenario 1, 3 units in scenario 2, so on and so forth. Now, can I construct a portfolio which can achieve this wealth in all these scenarios? If I can, then that's an attainable security. So that's a security that I can hedge against, right? That I can create a portfolio to manage, to control my risk. So I can talk about these attainable things.
LHL,
Mhm.
that's what you're trying to achieve.
Yeah, the left hand.
That's the wealth.
That's right. That's right.
Theta would be the amount of
Investments you make to achieve this. I want so much amount of wealth in each of those M scenarios.
theta.
Is there a portfolio which will achieve it? If yes, then theta is that portfolio. If such a portfolio exists, then the wealth X is attainable, right? So these are the risks which I can actually hedge against. The unattainable ones I will not be able to hedge against.
Right, so I understand. On the left side, what you have is the portfolio across all M scenarios,
Yeah.
right? So it's attainable if one of them needs to go. How is this?
So on the left, I have random variable, right?
Yeah.
Which takes you the wealth at omega 1 scenario, omega 2 scenario. Yeah.
Yeah.
In the right, I choose to make investments theta 1, theta 2, theta n. And I choose my theta in such a way that I exactly match X in all these M scenarios.
But are these X's given to us? We want to think of
Huh?
this X as a differently given. Oh, okay.
X is all those such X's I'm going to collect. I'm saying these are attainable securities.
But
Because for them, I can construct a portfolio and actually hedge that risk. Yeah. There's no maximizing issue happening, right? There's no optimization happening. But right now, we're not at that stage. So the point is simply, well, let's think of it the other way around. You can choose your theta 1, theta 2, theta n arbitrarily, right? And in this mathematical model, I'm allowing you those things. For all the thetas you can choose, you'll get some value in M scenarios in one time period later. Whatever you get, I say that's an attainable claim. And let me collect all those attainable claims. So those are the claims that I can achieve through investment in portfolios. Those are the risks I can kind of hedge against. Right now, I'm just saying this. There's no optimization going on right now.
so is theta unique?
For the same portfolio, need not be unique because N and M are different, need not be unique. Yeah. So X is equal to S theta, right? You'll have to make assumptions for uniqueness and all, so we'll talk about that later. Okay, so this is just a numerical example. So you have 3 securities here. You can see these values. You have 4 scenarios, and the first the value of the 3 securities are given as 1.033 and 2 in scenario 1. Their value in scenario 2 is as follows, so on and so forth in all the 4 scenarios. And now you can see that if you choose theta to be -1, 1.5, and 2, right? Then, if you multiply by the appropriate S matrix, you will see that this X here is achievable, is attainable. You get this value. Yeah. S matrix will correspond to these guys right here, like first security, second security, third security. This is for omega 1, this is omega 2, omega 3, omega 4. Yeah.
What is negative value in theta -1?
So then you're selling it, you're not buying, you're shorting it, yeah. This is for the first security. As you can see, the first security is a risk-free security. It's giving you the same value in all 4 scenarios. Okay, some more definitions. So we say that a vector pi1 through pi m, all positive, is a vector of state prices if the time t equal to 0 price p of any attainable security x is given by the following formula. So now we are assuming that this attainable securities can be priced, they have a price, and that price has this nice representation. So we have to show when that's the case. But suppose we can do that for every attainable security, then those prices we are going to call as state prices, pi 1 through pi m. Is this the kind of idea clear? Yeah.
So my X, WK, and all of these I get from S theta, which would be the set of all of the attainable securities.
Mhm.
And now the P thing, the P function, would basically give me the prices of all of these attainable securities at t equals to 0.
That's the hope, yeah. Once these state prices exist, so we are going to find out conditions when state prices exist. But once they exist, then price of any attainable security is given as follows. K equal to 1 to m.
And our states go from 1 to m.
Our states go from 1 to m. Yeah, that's
Wait, so then what we have is that I don't think how this will satisfy it for every. So this is satisfied for every single attainable security.
I'm saying suppose it is.
Yes. Okay. So the same pi 1 to pi m will be.
That's right. Suppose same pi 1 to pi m can be used to explain the price of every attainable security. Then we'll call those pi 1 to pi m as state prices. Right? So we're assuming a lot in this world. But later we'll argue that under no arbitrage condition, indeed pi 1 to pi m exist. So that's where we're kind of going with this. Okay? All right. So to simplify analysis, so pi k we're going to call as state prices. So I'm going to assume the existence of risk-free asset that returns 1 plus r at time 1. I need not assume this, but notationally it's much simpler to show things in this manner. In every scenario, for rupee invested at time 0. So for this theory to work, it need not be that the risk-free asset exists. It need not exist. You can just have, even the risk-free asset in 3 months' time, it has some kind of variability. So it need not be entirely risk-free, but that's fine. So theory will work. It'll be somewhat more demanding notationally, so I'm going to just ignore that issue for now. So now what's an equivalent martingale measure or risk neutral measure? It's a set of probabilities Q1 through Qm such that the deflated security prices are martingales. So discounted security prices are martingales, same as before.
We've already decided that 1 plus r would be equal to 1 in
Yeah,
order.
yeah,
And Q1 to QM is the probability of getting to state M.
yeah. Risk-free probabilities.
Okay,
Yeah,
so this is similar to the Q tilde and P tilde.
the P tilde and Q tilde we defined there. We said earlier that under no arbitrage condition, those P tilde and Q tilde existed.
Yes.
Now we're going to say the same thing. We've defined arbitrage very precisely. And we've defined all these strategies correspond to arbitrage.
Hmm.
If those strategies don't exist, then they must exist risk neutral probability measure.
Oh.
Then Q1 through QM must exist. And since Q1 through QM exist, pi 1 through pi m must exist.
Oh.
The state prices.
Yeah.
So state prices are just a normalization of Q1 through QN. Yeah, yeah. But state prices have a lot of charm, it's kind of what you get, unit amount you get in each scenarios. So they are used a great deal in economics. So it's good to talk about them as well. All right, so but what do I mean by a martingale? So this is discounted ith security at time 0. At time 0, my discount factor is 1. So it's just the same as the stock price. This should be equal to stock price of ith security at time 1 divided by 1 plus R. Right? Under risk neutral measure, this property should be true. This I'm going to call as S bar I. This is just the discounted stock price process, S bar I. So all I'm saying is that this equation must be true.
So the initial condition that we made about our risk-free rate was just valid for time t equals to 0.
I mean, I'm just saying if you have 1 rupee and you invest in risk-free security, you'll get 1 plus R in all the M scenarios.
Okay, except for the 0.
There is no 0 scenario. I'm starting at time 0, and at time 1, I have M scenarios. 1 rupee in time 0 becomes 1 plus R in each of those scenarios. I'm assuming such a security exists.
Just one.
Just one
There
security.
exists an ad. So I have an security. but
One
there
of them
exists
can
an
be
ad
this.
such That one of them
Yeah.
is a margin. With the discounted price of the margin.
No. One of them is a risk-free security. And now I'll say that risk neutral measure exists if I have probabilities Q1 through Q, so that this relationship here is true for every security. For every security.
That is the definition of margin.
That's right, yeah. So what I'm saying is that I have a martingale basically. So I have these new probabilities under which each and every security is giving me 1 plus R rate of return. So now it's not just one security anymore. Every one of them is giving me 1 plus R rate of return. So every one of those securities, once I discount by 1 plus R, I get a process which doesn't change on average. Now, all of this is it's less interesting if I just talk about one time period from now. But if I had multiple time periods, then this would be this property would have to hold for all time periods. Okay, so let me just define the complete market now, and that will complete the lecture today. So if every random variable is attainable, so that was the question that came up earlier, right? So if each and every random variable is attainable, for every x you can find a theta, right? Then your market is complete. Now, x is equal to s times theta. When can every x be attained?
X is full rank.
When s is full rank, right? So yeah, so that's when you get the complete market. So S is, your structure of what the stock prices will look like. It's your model for what the world will look like. If it's full ranked, then you have a complete market. Now you have to ask yourself, is that a realistic model of the world? Is it complete or not? But if it's complete, then we can do all kinds of fancy things. We can price every asset basically. So every option that you can come up with has a unique price without ambiguity. Right? If the market is incomplete, then some things can be priced, some things cannot be priced. Okay. So this is a result we are going to prove next time. So okay, just this one comment is also worth mentioning, that if a full set of elementary securities is available, then you have a complete market. Because if each and every elementary security can be priced, then every random variable x can be priced just by linearity. And the theorem we'll prove next time is, if an equivalent martingale measure exists, then there can be no arbitrage opportunities. I've defined what equivalent martingale measure is. If it exists, that means there cannot be an arbitrage in the market. Your S matrix will not allow for arbitrage. And we'll also go in the reverse direction. If there is no arbitrage, then equivalent martingale measure exists. So that's the fundamental theorem of finance. Sorry, say again. EMM. So that's a definition of EMM. Yeah, so I should have said that equivalent martingale measure is also called risk neutral probability measure. This is just two names for the same thing. So EMM is equivalent martingale measure. It's also a risk neutral martingale measure. Risk neutral measure. Yeah. Mhm.
Will we see the proof of this?
Yeah, we'll do this next time. Yeah. So we'll go through the proof of this properly.
This entire.
I mean, what you basically have to remember, what you have to see for the proof is this thing. So let me just say a few generic things here. That if I give you two convex sets that meet at a certain point, either they meet at a certain point or they are separated, I can construct a hyperplane that goes through them. That separates them basically. So that's going to give us this. That will imply that no arbitrage theorem implies that two convex sets have only one point in common. That implies that there's a hyperplane that goes through them, and that hyperplane corresponds to the risk neutral probabilities. So that's how this will follow. Other way around, risk neutral probability not applying an arbitrage is a straightforward argument. We saw it earlier, we'll see it again. So that's one thing I want to say to you right now. Other thing I want to say to you right now. So let there be light. No? Okay, there is. Okay. Just have to say it. Okay, suppose I give you an option like this. I mean, a security like this, S0, which takes value S1 omega 1, S1 omega 2, S1 omega 3, and I have a risk-free security which is, let me just make it at the top. A risk-free security which is 1 here, it becomes 1 plus R here, 1 plus R here, 1 plus R here. And now I give you an option which has a payoff, let's say, C of omega 1 here, C of omega 2 here, C of omega 3 here. Can we price this option? Or when can we price this option using no arbitrage principles? Let me put it differently. Suppose I have 1 and this becomes 1.05, 1.05, 1.05, and then I have a stock price, let's say, which is 100, it becomes 120 here, 105 here, 95 here. Suppose I give you an option which gives me 10 units at this time, 7 units at this time, 0 units here. Can I price it? Okay, how would you price it? What would you do?
They will solve the equation. They will solve that matrix equation.
How many equations do you have?
Because the last thing is zero, it doesn't really matter. Like this is two.
You still have to match the scenario.
Three equations.
Yeah, 2 variables, 3 equations. I don't know, do you guys see Sholay at all in your? But this is one of those बहुत नाइंसाफी है scenario. So you can't solve 3 equations with 2 variables. So you'll have to get extremely lucky that you solve 2 equations for 2 variables and third one is automatically satisfied. Then that's a good scenario. That's the only time. Then you get a unique price. Otherwise, you don't get a price of the option. But what do you get is the question for you. Yeah, so I want you to think about how do you get a good upper bound and a good lower bound to the option price in this world. In particular, do you understand linear programming? Have you seen that somewhere? So can you formulate a linear program which gives you these bounds? So that's something to think about. All right, guys, you've been very good. I was going to penalize you for 5 minutes, but I'll penalize you only 4 minutes. I mean, I'll only penalize you 1 minute. So we're going to call it off right now. You can go to your next class in a very relaxed mode. Any questions, anyone? Yeah, we'll start from next time. But we'll announce early on.
Yeah, I'll do that. I'll add orders, so like, you know.
All right, guys, have a good week. We'll meet next week.
It's not a program.
Okay, I'll ask
Even
you
the
to-
text to the